Welcome to our Clemson University Senior Design 2 final video presentation. Our project was the electrification of transportation via a single motor, dual wheel powered skateboard.
So some of the main motivation behind this project: the average market price for a 2,000 watt plus electric skateboard is around $750. Most, if not all of the current designs on the market utilize a single motor, single wheel drivetrain or a dual motor, dual wheel drivetrain. Each of these different designs has their own advantages and disadvantages. However, there is no current design out there for a single motor, dual wheel drivetrain that is the best of both worlds. So our objective was to build a 2,000 watt plus electric skateboard that utilizes a single motor, dual wheel drivetrain in order to compete with current market prices. So these are some of the project goals and deliverables. We needed a battery pack that could be attached and removed from the skateboard. We needed a remote control with its electronics fully encased that allows the user to control the skateboard at various levels of speed. We needed a motor that could turn a skateboard wheels for at least 5 minutes attached to the skateboard, and we needed the electric skateboard to travel 5 miles at a speed greater than 5 miles per hour on its own power. So here are some of our final design pictures. As you can see, our design is very clean and neat, and this is our final electric skateboard design. We decided to break up the electric skateboard system into 3 subsystems. We have the battery subsystem, the motor subsystem, and the remote controller subsystem. Here is a block diagram that describes their basic interactions. So to begin, we have some of our hardware design requirements. We needed the battery pack to be able to be charged and discharged and needed to output 36 volts and variable current to the motor controller. We needed a Raspberry Pi 0 to transmit analog values from 0 to 255 and a Raspberry Pi 3 to receive these analog values and convert them into a PWM signal to send to the motor controller. Also, the motor controller was to be sent variable power to the motor, and the motor had to drive the wheels and the mechanical drivetrain under the load of a human, specifically around a 200-pound human. And finally, the final design had to be electrically safe and robust.
To power the electric skateboard, we built a lithium-ion battery pack as seen in the pictures here. The battery pack consists of 30 18650 lithium-ion cells, which are rated at 3.6 volts with 20 amps of output and 2500 milliamp hours of capacity. The cells are then held together with nickel strips, and we chose 0.1 millimeter thick by 8 millimeter wide strips for the job. All the cells are soldered together using the Clemson Spark Lab. Along with the cells, the battery pack consists of the JBD Smart BMS battery management system. This is put in series with the cells in the battery pack and is responsible for protecting them during operation in events of things such as overcurrent or undercurrent or overcharge or undervoltage, and will shut off the pack in case any of those conditions are detected. This particular system is also equipped with a Bluetooth monitoring system, which allows you to see the real-time voltages and activity of the battery pack from an app on your phone.
We designed this battery holder to snugly and safely hold the battery pack and the BMS to the board.
Screen below, there are 2 photographs of our motor attached to our 3D printed motor mount with the drivetrain that consists of 2 bevel gears and 2 gears with pulleys that connect to the wheels. As seen in the photo, we utilize a Hobby Sky 6374 brushless motor. This motor is rated at 3600 watts. However, we only utilized 2160 watts with our current battery setup. The motor controller utilized is the VESC 4.12. The reason why we selected this motor controller was as it was easily programmable to our system. The mechanical drivetrain utilized 2 bevel gears, one that would connect to the motor and one that would connect to the D shaft, which was our drivetrain. This drivetrain D shaft was manufactured at the machine shop at Clemson, and in the center there's a 10 millimeter bore. Meanwhile, the ends were shaved off to 8 millimeters to incorporate our gears ordered to connect the pulley of the wheel to the drivetrain.
Hardware design for the motor also consisted of 3D designs and circuit diagrams. The circuit with the motor that had the Pi 3 that supplied a PWM signal with a pull-down resistor circuit connected to a motor controller that fed to the motor is seen below. This is all powered by the skateboard battery pack. 3D designs were made in SolidWorks. Featured is the drive shaft that was created by the Clemson machine shop. Next is a motor mount that was 3D printed in the makerspace using PLA material. This piece holds the motor in the back, and in the front it stabilizes the gears, drivetrain, drive shaft, and pulley system for the skateboard. Lastly, discs were 3D printed. They allowed the gears to be torqued onto the wheel. The hardware design for the controller had a Pi 0 powered by a portable battery pack, and it had a pull-down resistor circuit. The Pi 3 was housed in the underbelly of the skateboard, while the Pi 0 was housed in a 3D printed remote control casing, as pictured here. This casing also had a lid to it, as you can see here.
For our software design, we wanted to transmit an integer value ranging from 0 to 255 across Bluetooth at least 10 times per second. This was so the other Raspberry Pi would be able to output an 8-bit pulse length PWM signal to the motor controller at least 10 times per second as well. For our software design, as previously mentioned, we used Raspberry Pis and the use of Python to generate PWM signals and to connect the two Raspberry Pis via Bluetooth. Here's a flowchart outlining how the software works on the handheld remote. The program initially runs once the user powers on the remote, and then a Bluetooth connection is established with the board via MAC address. Next, the program continuously listens for an analog input from the button and sends an integer value to the board via Bluetooth, signifying the duration of the current button press. This part is continuously looped for as long as the remote remains on. Here is a flowchart signifying how the software on the skateboard works. The program initially begins once the user powers on the skateboard, and then immediately a Bluetooth connection is established between the remote and the board via MAC address. Immediately after, the board checks for a Bluetooth signal from the remote, and if the signal received, then a PWM signal is sent to the motor based upon the received integer value. If a signal is not received, the board continues to search for a signal. This program is only stopped once the board is powered off.
Here is a little bit about the methodology behind our drivetrain, specifically the gears that we chose. So our shaft gear has 16 teeth, our wheel gear has 32 teeth. This results in a 1-to-2 gear ratio, where 1 revolution of the drive shaft is equal to half a revolution of the wheels. So advantages of electric motors include instantaneous torque and high RPM. However, if the torque is too great, an electric motor will burn out instead of lock out. This gear ratio takes advantage of high RPM while protecting against a burnout by reducing torque on the system. So here begins some of the discussion of our results. These first videos show each one of us riding the electric skateboard down a hallway. This last video gives you an idea of what the drivetrain looks like when it's spinning. Overall, we had a very successful project. Here is a graph from the VESC software. This test that was conducted involved spinning the wheels at a 5% duty cycle over here and a 10% duty cycle over here. And as you can see, different current was required for each of these duty cycles. This served as a proof of concept that our electric skateboard was functioning correctly. Here is a graph that has time versus weight. Because each of our teammates had variable weight, we thought it would be neat to plot our weight against the time it took to travel a specified distance on the electric skateboard. And as you can see, the heavier the load, the longer it takes for the skateboard to reach a desired speed.
So through this project, we were able to successfully develop a 36-volt, 60-amp lithium-ion battery pack built as I discussed earlier. And below shows 2 screenshots from the app I mentioned of the battery pack both charging and discharging. The pack can successfully output up to 60 amps thanks to the battery cells we used and is rated for 36 volts. This project had a few challenges and bottlenecks. One of the biggest ones was cost limitation. A lot of our parts, we 3D printed them using plastic because CNCing them was just not in the budget. This led to potential structural deficiencies, for example, in the motor mount, which is responsible for handling all the torque of the motor, and it's currently made out of plastic and would definitely benefit from being made out of aluminum or some other metal. Another issue we had was knowledge scarcity. When building the battery pack, the nickel strips we used, there aren't any certified or guaranteed testing that's been performed on nickel to determine accurate capacity based on surface area. So currently, the battery pack's safe rating for current is unknown and is most likely inadequate given the amount of nickel in it. Another issue with the battery pack was a lack of tooling. Similar to the cost limitation with the CNC, we don't have a CNC machine, but we also don't have a spot welder. When building battery packs, we chose to solder the cells, but ideally you would spot weld them. It's a much more common method used when building battery packs and is a lot safer. Finally, niche part requirements. This can be seen in the custom drive shaft we had to have machined because the part just didn't exist to be purchased due to the precise and particular dimensions that we required. While we were able to successfully develop a prototype, there are still areas of improvement on it. Some of them are the sound of the system, current control, and a refined remote. So the drivetrain is very loud right now due to the metal-on-metal bevel gears inside it and the high RPMs of the motor. To fix this, we could redesign the motor mount bracket to incorporate some form of shielding around the gears or add sound deadening material within the bracket. For current control, the battery pack is currently underpowering the motor. The output of the cells is lower than what the motor is capable of, so adding cells in parallel to the battery pack would allow for a more powerful motor while also a more range and capacity within the pack. Also with the battery pack, the nickel strips we use to solder the battery packs are rated too low for both the cells and the motor. To fix this, we would just need to solder more nickel strips between the cells to increase the thickness and the current rating of the pack. Finally, the remote is currently very large, and we could fix this by shrinking down the components all into one board or using different components that are smaller. Another thing we could fix with the remote is to use a potentiometer instead of a button for the input to allow for more precise manipulation of the throttle and the current output of the motor.
And finally, this brings us to the end of our presentation and some of our conclusions. Our intended operational goals were met with the performance of our electric skateboard. However, the expected cost was missed. It was missed by around $100, and this was mainly due to the customization of the drive shaft that was necessary. If we were to redo the build, further research would be done into the safety of each component, and their ratings would have been performed. And finally, we'd just like to say that our team successfully applied many electrical and computer engineering skills that we learned over the course of our college careers at Clemson University. Thank you very much, and we appreciate your time.